Oh, it's your daughter?
Yeah.
Great, it's very cute.
She has my hair too.
Okay, everybody. We will go to our last invited speaker section. So right now, I am honored to invite Professor Taylor, come from the University of Alberta. And he is the director of the Intelligent Robot Learning Lab and also the Canada Katia AAAI chair, and also chair in the AMNIA, right? Okay.
All right, good afternoon, everyone. Thank you for coming back from the coffee session. I appreciate it. My job, or at least my goal today, is to try to be a little provocative. So where do rewards come from? And I need to be in PowerPoint. There we go, maybe? Good. So we know reinforcement learning is amazing. We have an agent that interacts with an environment, gets rewards. Where does the reward come from? Yeah. So really, we just, as a reinforcement learning person, we assume that someone hands us the reward function. It is correct. It is available. It is what you're doing. It defines the task. It is your utility, as Ben was saying. So the question is, where does that thing come from? So today, I'd like to present very briefly a couple ideas. The first one is rewards come from people. So we should acknowledge that and think of it as a human agent system. The second thing that I'll talk about is maybe there is a well-defined reward function, but we can't always see it. Then what happens? So let's talk about the first one, where we're thinking about where does this reward come from? My friend Brad Knox is at University of Texas, and he had a paper in AIJ where they were showing how people had designed reward functions for self-driving cars, and there were some problems with them in a bunch of different papers. And he went on to present a paper at AAAI a couple years ago talking about the perils of trial and error reward design. So this is a good paper. I suggest you check it out. But here in this paper, what he argues is that, say, okay, let's just a question for the class. If you want to get an agent to do something, you want to design an objective, how might you do this? So one thing that many people do is a trial and error process. So first you say, I'm going to take a guess, I'm going to write down a reward function, and then I'm going to train my RL agent to learn. Now, of course, those of you who do know RL, you try to train and it doesn't work. So you have to go and change your hyperparameters and then change your neural network. But let's ignore that. Let's just say you train once, and it only takes a day. So then you train and you look at the agent as it's learning, after it's learned, and darn, it doesn't do what I want. So now I'm going to go and change my reward function. I'm going to tweak my reward function, retrain, and iterate. So this is going to be slow because you're doing all of this training, but more pernicious, you might be introducing bias here. So what Brad did is he went to 8 papers who were doing this autonomous driving, and by talking to the authors, they all used trial and error design for their reward function. He also went and talked to a bunch of practitioners, and most of them also did this. So why is this trial and error bad? Well, you can think about over time, you're making new reward functions and your performance is getting better. The problem is you might think, well, this is true in this context, but really, if I'm defining an objective, that's the task. Here, I'm iterating over training, which depends on the agent. So what could happen is if you change the hyperparameters, if you change the agent's algorithm, you could now, because you have fine-tuned your reward function to this particular context, your performance can actually go down. And it turns out his paper is showing out how this happens and why this happens. So this is bad. So what we'd really like to do is come up with a better way of designing a reward function. How do we get a reward function out of a person? Because that defines the objective, that defines the utility for the agent. And I am happy to say, stand up here and tell you all, we have started down that path. We haven't figured it out. So with Brad and my student Callie, lecturer at Princeton Suyog, and Serena, who's starting at Brown this fall, we've made some preliminary progress, and I wanted to tell you about it because I'm excited about it, but also to get your feedback. And our ultimate goal is to come up with tools and procedures so that we can elicit a good reward function for a task. Now, as the first step, what I'll tell you about today is a little bit simpler. Instead of asking people to design a reward function, we ask people to select between reward functions. So one thing you've probably seen is people are using LLMs to define reward functions. So you can give the LLM, like, this is my task. You know, I've got a self-driving car and I need to balance between a fuel efficiency and safety. What would a reward function be? And an LLM could spit out a bunch of those and maybe iterate on them. But then how do you get a person to say, that's the one I want? So ideally, you all have probably heard of alignment. The way we think about alignment is that a reward function is aligned with a human if it does what they want it to. So it's a little circular. But we're thinking about the reward function is aligned, not necessarily the agent that's trained on it. Because if we can think about just, is the reward good, rather than having to iterate over the training cycle, then we could go a lot faster. There's also a few methods for measuring alignment in the literature, and they often rely on having the true reward function. So you can say, how well aligned is my reward function with the real one? Now the problem, if you already have the real one, what the heck are you doing with this other one? So we wanted to take that out. And we're going to also, I don't go into the details, but the method we use is also invariant to potential-based shaping. So if you have a well-designed reward function, then you can add in shaping rewards and this metric won't change. So here's the setting. Instead of the MDP being provided to you, in the real world, an RL nerd like myself needs to define the MDP. So I need to write down a reward function. I'm not an autonomous driving expert. I'm not an airplane pilot. These are some of the domains we work in. I can't know what a good reward function is, but I've got access to a subject matter expert. Now, of course, that subject matter expert probably doesn't really understand RL or reward functions, so we need to fix this disconnect. What we decided to do is have the subject matter expert give us preferences. So you're probably familiar, many of you familiar with preference-based learning. You can say, given these two trajectories, which one do you like better? Or in some cases, do you like them the same? So we can get a bunch of trajectories and have the person make pairwise comparisons or rank them. And then we're going to take this ranking and we will then look at the difference between the preferences the subject matter gave us and the induced preferences by our reward function. So remember, we've written down a reward function. So I've got two reward functions, and I can look, if I've got some trajectories for each of these reward functions, I can look at the return of these different trajectories according to each of the reward functions. So I can look at all the returns of these trajectories, sort them by returns, and then I can see how this sorted list corresponds to the preferences of the person. So let me give a more concrete example. So for instance, in the autonomous driving case, on the left, you see the human stakeholder might have said, well, there's four trajectories. The best is success. The second best is if the car doesn't move at all. Third best is 90% of the time you succeed and 10% of the time you crash. And the worst is you crash. So we could write down a reward function. And it turns out when we use this reward function, we get a return of 10 for the top trajectory and then 0, 4, and negative 50 for the other three. And in this case, there's a mismatch. So the human would prefer idle over the possible crash, but the reward function would prefer the possible crash over idle. So we've got this alignment metric that goes from -1, which is completely opposite, to +1, which is perfect. So here's an example. Again, let's say I've got 3 trajectories, A and B. With the human, our A is preferred to B, but with our reward function, with a certain discount factor on the right, B is preferred to A. So we use what's called Kendall's tau, and Kendall's tau is a way of measuring this mismatch between ranked lists. So in this case, it has something to do with the number of pairs that agree and the number of pairs that don't agree. So in this case, we've got, oh, whoops, I mixed that up. But we've got 1 that does match and then 2 that are discordant. So 2 that don't match. And in this case, we end up with a value of -1/3. But that is a way that we could evaluate this function, this reward function, and we could choose another reward function and see which one is better aligned with a human. So we get this, we get trajectory, we get preferences over trajectories, we sort them, and then we get a number between -1 and +1. We looked at this domain called hungry thirsty. Some of you might have seen it. You get rewarded if you are eating and you're not thirsty. So at least I can relate to that. I don't know about you. But it's kind of interesting because there's a bunch of different ways you could formalize this reward function. So in our recent user study, we considered 4 different cases. The first case is we're just going to show the human 2 reward functions and say which one do you prefer. Spoiler alert, they're not very good at that. When you just show people 2 reward functions, it's kind of hard to say which one you'd like better. What works much better is if we give them the reward functions and this metric. So pretty quickly, most people realize, oh, the higher this number is, the better, the more aligned the trajectory is with the preferences. And the third thing we can do is give them the reward function, our metric, and a visualization. It's actually similar to what we see on the left. We show the alignment between the preferences and a reward function. So this extra visualization is actually superfluous. But, you know, some people like being able to visualize, so we threw it in there. And then we asked a couple of questions. So the first one is there a perceived benefit? So does the person think that it's, which of these cases does the person like more? Is there lower workload? Is there higher ease of use, better understanding? And then there's also the practical benefit. Does this actually let them choose the right reward functions, and can they do it faster? So we did a 10-person user study, and we see that overall, the reward function, if we just give them the reward, the bars in blue, we see that the workload is higher, the effort is higher, and then over on the right, their confidence is lower, the ease of use is lower. So we see that if we provide them this metric, that they're able to, they like it more. Now, what was interesting to me also is that the visualization didn't make a big difference. So even though we were giving them all of this extra information that they didn't really need, the users didn't mind it. So then the second question, is there a practical benefit? Here we do see, if we look at the time taken. So what happens is people who are just looking at the reward function, even though it's very little information, they spend a long time making their decision because it's just a really hard, difficult task to try to understand 2 reward functions and try to figure out which is better. We also see that they spend a little bit more time when they have the visualization. So you could say, well, maybe we just want to show them this alignment metric. Maybe we don't need the visualization because the visualization slows them down. But some people in our qualitative results, some people actually like the visualization. So we're going back and forth trying to figure out exactly how to use this. But the important thing is this metric helps them choose better reward functions faster. So where does that leave us? This work was looking at introducing this metric, which is based on preferences. So again, the subject matter expert does not need to give demonstrations. The subject matter expert doesn't need to write down the return of a trajectory or give a reward. All the subject matter expert has to do is choose, I like A over B, I like C over D, and so on. And then given this metric, we are able to have, well, I guess they're semi-trained humans. We took mostly graduate students who had done some reinforcement learning, and they were able to use this metric effectively. Where we'd like to go next is thinking about what if we want to construct a reward. Instead of choosing between two rewards, what if I actually want to sit someone down and say, okay, what are the reward features? What are the weights over those? And actually have them build it out. So that'll be a more difficult UI, more difficult problem. Also, this was in Hungry Thirsty, which is a nice toy domain, but we would like to do something more interesting. Because where we want to go with this is, again, coming up with a better way, a more principled way of getting good reward functions that reflect what a person wants the agent to do. Okay. This was the first part of the talk where I tried to argue that maybe the reward function you're handed has to come from a person. Now, another thing you might think about is what happens if you can't always see the reward function. So this is something that Mike Bowling has been working on for a few years. Our student Ali Reza is a master's student, Monta is a PhD, and Simone is a postdoc. And we've been thinking about the case where there is a reward function, but the agent can't always access it. So for example, let's say you've got a robot that is in your house and waters your plants. You know, good job, robot. You don't want to overwater the plants because then they'll get damp and moldy. You don't want to underwater them because they get dry and unhappy. But now, how does the robot know if it's watered the correct amount? And so one thing it could do is there could be a smart home, right? So the smart home has these sensors and it's telling the robot exactly how well watered the plants are. But then what happens when the smart home goes down or those sensors fail? The robot can no longer get the reward, but there is still a reward. Just because you're not reading those sensors doesn't mean you're not killing the plants. Or you could think, well, maybe I have, the robot has a little probe. So the robot can water and then stick the probe in and it waits about 5 minutes and then gets a reading. Well, even if the robot doesn't take that measurement, there's still a reward for whether the plants are watered or not. Another thing you could think of, if maybe the robot can only see how watered the plants are when the lights are on. So if the robot's watering the plants in the dark, there's still a reward. So the goal of this work and the goal of the agent is still going to be to maximize the reward, even if it's not observed. So we're in a setting where we can't always observe the rewards. And in some cases, you may need to act to observe the reward. So maybe you need to go and turn on that light switch. And there's some kind of process. So maybe the robot knows that if it goes and hits the light switch, the light will turn on and it can take a reading, or maybe it has to learn that. And it could be deterministic or stochastic. So maybe you go and flip the light switch and the wiring isn't great in this room. And sometimes you've got to flip it multiple times, or maybe sometimes there's a power outage so the lights don't turn on at all. So we call these monitored MDPs. So now one of the first questions we get is, oh, okay, monitored MDPs, you don't always see the reward. Isn't that just like, and then there's like 15 things that people list. So this isn't a POMDP because we're assuming the state is visible and it's the rewards you can't see. This is different from sparse rewards because in a sparse reward setting, you just have an uninformative reward, like you get a bunch of zeros. But we're saying you don't even get the zero. You don't get anything. So if you're interested, I'd be happy to go more into why this isn't something else. This is actually something new. And the formalism is instead of having an agent that interacts with the environment, now there's this extra thing in between. Now there is a monitor. So now the agent takes an action in the environment and may take an action in the monitor. So this could be turning on a flashlight or asking the smart home for a reading. And then there's a next state in the environment. There's a next state in the monitor. There's a reward from the environment that the agent can't see. The reward, which here is R superscript E, goes through the monitor, and in some cases, or it goes through the monitor, and then the agent receives the reward from the monitor and the reward of the environment with a little hat. So reward of the monitor, this could be if I turn on the flashlight, I'm using some electricity. Or if I call Matt to ask if the plants are watered, he gets annoyed and I have to pay him $5. So there can be a cost for using the monitor. And then there can be, if the monitor is enabled, I can see the environmental reward filtered through that monitor. So in some cases, if the monitor is off, if the light switch is off, then that R hat E will just be bottom. So that's saying I don't know anything about the reward. Or for this talk, let's just assume the two choices are either I get nothing or I get the correct value. You could also make this harder and say that the monitor could also add some noise or do something different. But now so if the monitor is on, I get the real reward. If it's off, I don't get any information. So the agent observes these two quantities, the reward of the environment passed through the monitor and the cost from the monitor, and it's trying to maximize the actual environmental reward and the monitor reward. So it's still trying to maximize the discounted expected sum of future rewards, but now it's trying to maximize the environmental reward and this extra cost thing, and the trick is the agent doesn't actually see the environmental reward. It only ever sees R hat E, which is either the real environmental reward or nothing. So this ends up giving us kind of a problem space. So for instance, we can say, well, we've got this big class of mon-MDPs, and one particular set of instances are MDPs. Those are exactly the monitor has cost 0, and the monitor always gives you the environmental reward. So our mon-MDPs are reducible to just normal MDPs. But then there's also the case of solvable MDPs. So this is the case where I can go and do stuff in order to see the reward. And then once I learn about the reward, I can figure out how to act and maximize this thing, just using normal-ish reinforcement learning stuff. Where this gets really interesting is think about the hopeless case. If I can only see the environmental reward by turning on the flashlight and my flashlight has no batteries, if I can never see the environmental reward, it's just hopeless. It feels like you're in grad school again. If there's this one case where there's just nothing you can do, but the interesting case, which I won't really get into today, is the unsolvable case. So think about there are some places that I cannot see the reward. What should I do? Well, maybe the safe thing to do is just avoid those states if you can, right? If I'm walking around a grid world and there's one cell and I don't know if that cell contains a bag of gold or a crocodile because I can never see the reward there, maybe I should just avoid it, play it safe. So here's an example of one mon-MDP task. So here we have an agent that there are these poison clouds that if it is monitored, then it knows to avoid those poison clouds and try to get to the goal. So actually, let me just go through. Let's just look at the one on the left. So here there's 9 states. The agent can go up, down, left, right. It can ask to be monitored. It tries to get to the goal and avoid the toxic waste. But if it is monitored, if it turns on the flashlight, there is a cost. So what are some of the simple things you could do? One thing you could do is say, anytime I get no information from my monitor, I'll just say that's a reward of 0. Well, in that case, what the agent will do is turn the monitor off, so it gets a reward of 0 when it's in the poison, and then turns the monitor on as it's walking to the goal, it walks to the flag, and it gets that plus 10, or that plus 1. So that's not very good, because so if the agent just says, oh, if I don't ask to be monitored, then the reward doesn't count. But that's not a good model of how the world works. Another thing you could do is just, if I don't get information from my monitor, I won't do the queue update. So in this case, the agent will turn the monitor on and learn to walk around to get the flag. However, this means that the agent is always paying that cost for each time step. And you would think that once the agent learns the reward, it would just learn to do this without paying the monitor because it already knows the reward. So the final thing that we did in this AMOS paper was to learn a reward function. So here, the optimal policy is once I have used my monitor to learn this state space, the agent has learned to avoid the poison and gets to the flag, leaving the monitor off. So we go through a few of these different, we've got a number of different algorithms, we've got a number of different tasks, and show that we can do reasonable things to try to make progress and have the agent act reasonably, even if it has to be clever about explicitly reasoning about the reward, because it's not always visible. So where does this leave us? As I'm wrapping up in my final time before questions. So this MonMDP setting, we now have 4 papers. This is only the first one in the series. But we've got this series of papers where we have this the novel formalization where there is a reward, but you can't always see it. In another place you might see this is think about train and deploy. So if you train your agent in the lab and then deploy it in the real world, maybe there's not someone who can give you that reward signal, but you still want the agent to act appropriately. We've got a number of algorithms for solving these MonMDPs, and our latest work is looking at how to have a model learning method. So we can think about planning to go and explore in order to find rewards. All right, so if you found any of this interesting, here are the 3 main papers I mentioned. But what I was trying to do this afternoon is to encourage you to think beyond the MDP framework. Here are 2 ways, either thinking explicitly about rewards coming from the human, or maybe the rewards aren't always observable. But there's many different ways where we can push at or change or question the MDP formulation, and I encourage you to do that. What we talked about today was thinking about who designs rewards and are they available and all of that. But really, I mean, there's so many interesting problems out there that don't necessarily fit perfectly into an MDP. So just be aware those exist, and hopefully this will generate some discussion. Now, don't be like me. You should stick around for the next talk because Kevin's awesome, but I have to run to an interview for someone who's interviewing at University of Alberta. So I can stay we've got about 4 minutes for questions, but then I need to hustle to go to an interview. So if you have more questions, I'll be around tomorrow, or you could email me. Thank you for your attention. No questions, good. No, there's pushback. Yes.
The cost of the monitor, for example, right? Because that is obviously very important.
Yeah.
In the formalization. So is it God-given also?
Yes, God has given us the monitor cost.
Okay.
That's a good point, because we're assuming that if I turn on the flashlight, I know how much the battery is draining and how much that costs me. Exactly.
Yeah. So now the other thing is there, I think to me, this is an opportunity also for multi-agent
Yes.
reasoning, right? Because now instead of having the monitor, I can have my little buddy that now can help me.
Yeah.
And so now my little buddy has its own reward, right? In terms of helping me and when to do that. And so then we get into these incentives and costs and all that kind of thing.
Yep.
So that's a very, kind of interesting thing. I will go and see the scout. I mean, yada, yada, right? But that is one thing. And the other thing is, in terms of the ranking for the initial thing, there is in the operations research, you probably know that there is this preference elicitation, which is very problematic. And if you ask people can be self-contradictory or going to cycles.
Yeah.
So you say I prefer A greater than B, greater B to C, but C to A. And so here I am in cycles and I can never break the cycle. And also decision makers now, probably you know that, but I think I'm saying that for the, may change their mind. So you ask a decision maker, where would you like to put this hospital, or we are committee or something like that? And they say, well, this here, here, here. And then you ask them maybe next week, and maybe something else had happened. They thought about cost, or I don't know what. But the problem is that they are not consistent with what they told you last week. So this is another kind of moving target kind of situation with talking to humans. And a last comment is, have you thought, and because I know that there is some work from people like Alberta, who is considering putting, reasoning, formal reasoning in actually proving that particular words are going to work. So this comes, of course, from hybrid systems theory and so on, where I have the requirements for my system, but I want my requirements to be correct and not have contradictions, things and so on, and think about the consequences of that. So that's another literature that I think would be very useful in this reward alignment.
So responding briefly in reverse order, it would be great. So if we could actually, have the right constraints and have a way of proving optimality, that would be awesome. You're right that people are self-contradictory and they're non-stationary, even if they're rational. But so we're just assuming we can get those preferences because we're not going to solve everything. The last thing, and yes, the monitor is its own agent. That's how I justified to myself why I could talk about this in this workshop. Because you could think about that monitor. I mean, we know Maria doesn't like people, but I like people, and I want the monitor to be a person that has a real cost, or it could be a buddy that you trust, an agent that you trust that has some costs and needs to act, and maybe it's busy, and maybe it doesn't care about you today. Getting some really interesting stuff. So I'm super excited about that. All right. Oh, do we have time for one more?
So my question is very simple. The monitoring, right? How does that affect like the exploration versus exploitation? Would it? Sure. So my question is, how does the monitoring affect like exploration versus exploitation that we usually have in RL settings?
Yeah, great question. So what I didn't go through is on the right, there's a button environment where you have to press the button to turn on the light. So in this case, if the light is off, your exploration doesn't really help you because you're not getting the rewards. But eventually the agent learns to go down and press the button so that it can see rewards. So in order to explore, it first has to turn the light on. So you need to, and then if it wants to learn about the reward in the, in the upper left state, it needs to go down to the button, turn it on, and then come back to the upper left state. So now that exploration has a temporal component to it. So you really do kind of need to think ahead in order to explore efficiently. So the short answer is now the monitor makes exploration a lot harder. All right, thank you again. And apologies, I have to run out, but you should stay. Kevin's awesome.
Can you try again to stop sharing and sharing again?
Let me try otherwise the display. No, it's actually
Yeah, you can use my computer. Yeah.
But I really don't want to because I think it has many embedded fonts.
Yeah, no problem, no problem.
Right.
Yeah, yeah.
So.
Send me your.
Are they sending it to Alberta?
sure.
Send to the friend or send to me. Also okay.
It isn't possible to plug it in and we don't worry about it. Is there any on it?
No.
There's actually one person,
Yeah.
but I guess I can also like, we can plug it in and you can stay on Zoom. Let's share this.
Okay,
Yeah.
that's true. Why don't we do that? That's
Yeah.
all.
Let me see. Oh, is this one? Yeah, so you can come over here and you have an HDMI?
Yes.
But I believe the record is record that computer.
That's okay. I think the. It's not worry about it.
How are we doing?
Okay, okay.
All right, look at that. You can hear me okay?
But I show in the.
Yes, I would mind, and I'll tell you why. I actually had a medical emergency last night. I slipped on some ice and I cut up my face.
Somebody.
So this is actually not for respiratory problems. This is so you don't have to look at my face. So I think that's to be preferred. But yeah, sorry about that. I'll just stand close to the mic. Here's hoping that that works okay. All right, well, sorry for the chaos. Let's get into it. So I want to talk about using machine learning for human-like strategic reasoning. And let me get a time check. How long should I be targeting here?
30 minutes.
30 minutes? Okay.
Fine.
Great. Okay, so I aim to tell you about 2 different lines of work. We'll see how it goes. If I end up telling you about 1 line of work, that'll be great too. We'll just see what happens. I would be very happy if you want to interrupt me with questions. I think it's more fun if we kind of have a dialogue. So just stick up your hand if you have something to say, and let's just talk to each other. So this initial line of work is primarily with James Wright and Greg Dion, and then some other students over the years have also participated in the project. So here I want to think about behavioral game theory, which many of you probably know that I've been working on for a long time. I'm going to kind of contextualize the broad sweep of how I look at it, and then I want to tell you about some very recent stuff that we've been working on. Game theory, as you know, is a sort of beautiful statement about how agents would reason in a strategic settings, but it makes sometimes very counterintuitive recommendations that don't really align with what we actually observe humans to do. And so we can conclude that the world must not be populated only by perfectly rational agents. And that means if we want to make good predictions about the play of unsophisticated humans, then we need a model of human behavior. And in the context of this workshop, modeling humans is really important if we want to build systems that work together with humans, because it's going to be necessary to make some kinds of forecasts about how humans themselves reason. And if these forecasts are really flawed because they're based on kind of Cold War thinking from game theory, then we're going to be off to a bad start. So that's the sense in which I think you should think about this topic. So behavioral game theory, as you may know, is an area within game theory that essentially treats the problem of coming up with a strategic model as a machine learning problem, rather than as a sort of thought exercise that one would carry out analytically. So in particular, what we want to do is, given an arbitrary game, and that's really important. I really mean an arbitrary game. I don't mean I want to study the heck out of an environment and know what people do in that environment. I want a model of how people reason, right? The nice thing about game theory is you can use it anywhere. It might be wrong, but you can use it anywhere. We would like to find something equally general, which is less wrong. So I want to take as an input a game and then make an output that says, for one particular player in that game, what do I predict that player would actually do in the game? And I predict that as a probability distribution over that player's actions in the game. And then I'll evaluate the model by assessing its generalization performance. And by generalization, I mean showing it now another game that it wasn't trained on and seeing, like sort of held out data and seeing how the model is able to predict human behavior there. And if I can do that well consistently across held out games, then I'll say that I've captured something about human performance. So how do you decide what human performance is? It's kind of the Achilles heel of behavioral game theory is coming up with the data that you would want to do this machine learning on. So in particular, we just kind of combed the literature. I'm going to focus here on unrepeated simultaneous move games, not because I think these are the only important games in the world, but because these are the kind of simplest setting to study. And already this is a pretty challenging setting to do a good job with. So we kind of want to figure out the methodology in the kind of cleanest place. Some of our current work is trying to go beyond this, but we looked at unrepeated simultaneous move games, and we looked at the literature where basically behavioral economists around the world have paid lab subjects. They've gotten human subject research approval. They pay them game by game to get their to ensure that the players' utilities actually correspond to the utilities that they want them to be, and then they observe how they play the game. And then they do in fact pay them. And then in this way, we get these data sets that contain between 8 and 200 distinct games each, and sort of between hundreds and thousands of distinct observations of somebody having played a game and then gotten paid. And we took all of this stuff, basically everything we could find from 1994 to 2023, and we just put it all together into a single data set. We normalized for payoffs. And so the challenge that we want to set ourselves is for these 366 different games that people have ever showed to humans, so lots more than just Prisoner's Dilemma, all kinds of different stuff, and 26,000 plus observations of somebody playing a game. I want to try to build a model that somehow finds patterns in that. Now, I said, so now let me start to make some comments about newer work. All of this said, I guess on the previous slide, that I want to evaluate models by assessing their generalization performance. To be able to make a statement like that, I need to know what I mean by performance. I need some way of scoring how well you did. And again, remember, the task here is to predict a probability distribution, but then to observe a sample from that distribution. And so it's a tricky thing because if I predict the uniform distribution and the answer that was right, it really was the uniform distribution, I'm still just going to see a point mass on one thing. So scoring is not completely straightforward. Probably for this reason, it turns out that the behavioral game theory literature has very far from agreement on which loss function should be used to fit these kinds of models, the people who do this kind of work. And so even if you're otherwise not that interested in the problem that I care about, but if you have something that looks like this, where you're observing examples of human play, the predictions are probability distributions, and you want to know how to score an ML model, this paper from AAAI last year is something that might be of interest to you. So we made a principled axiomatic argument about which loss function is best to use. And we argued that loss functions of this kind that try to explain how people play, how people act in experimental settings where we only observe discrete actions, should satisfy 5 different axioms. The first 2 axioms are what we call alignment axioms. And these are axioms that say that the loss function should induce the right preferences over predictions. So if you're familiar with the scoring function literature, these are like propriety axioms that say that you have to have a proper scoring function. The difference between these and propriety axioms is that scoring functions typically don't allow for the possibility that the generating function is something that isn't in the class of functions being learned. So this is a kind of generalization of propriety axioms to that harder case where the function itself might be misspecified. And then we have three other axioms for interpretability that say the loss should not depend on the number or the order of the observations. As the empirical distribution gets closer to the prediction, there should be lower loss. And a perfect prediction gets a loss of 0, so just a normalization. With all 5 of these axioms, let me show you, here are some of the main things that different people have used: negative log likelihood, error rate, mean absolute error, cross entropy, KL divergence, Breyer score, squared L2 error. These are all things people have published on in the literature. And indeed, in our own past work, we used negative log likelihood, but we were always unhappy with it. And in particular, we were always unhappy with the fact that when we changed the sizes of games or the numbers of observations, the loss units changed, which made them very hard to think about. So our paper, in the end, doesn't say that there's only one loss function that you can use. It actually shows a class of functions, which we call diagonal bounded Bregman divergences, and says any of them satisfy all of our axioms. But among these different loss functions that people have used in the past, only one of them happens to satisfy all of our axioms, which is squared L2 error. And so that's the one that, so way to go, Ori Plonsky. He's the only one from the literature who actually used this loss function. We're switching over. It's easy to do, and it has these beneficial properties. So that's what we're going to do here. And that's the first plug I wanted to make for some recent work. Now let me tell you a little bit about how behavioral game theory models work. So how many people here have heard of quantal cognitive hierarchy models? So it's kind of cool for the rest of you who either don't know what they are or just don't want to raise your hand, and you're going to find out again anyway. Here's how they work. They're kind of neat. So remember, I'm going to show you a matrix game. And what I want is for you to make a prediction about the probability distribution over what player 1 is going to do. And the quantal cognitive hierarchy model does this by combining 2 ideas. The first is, it says you don't, game theory says you best respond. You solve the optimization problem against what your opponent is going to do, and you play whatever action is the best action for you. Kind of makes sense, except what if there's some actions are almost equally good. Maybe people are not quite so reliable as to exactly maximize. Quantal best response basically says that players play a soft max against all of the utilities that they can get. So it says, this came from experimental economists, so they didn't call it a soft max, but that's what it is. They're saying, basically, if 2 actions have almost the same utility for you, but one of them's better, you're still going to play them with almost the same probability. And if something else is really terrible, then you're going to play it not 0, but almost not at all. So that's the idea of quantal response. It basically causes the probability distributions to always have full support. The second idea is what we call iterative strategic reasoning. And it says, let's imagine a kind of fictitious agent that we'll call a level 0 agent. These are agents who behave non-strategically. And they're going to be very important for the story I want to tell you going forward. So pay attention to this bit about level 0 agents. So level 0 agents are going to do something non-strategic. What do I mean by non-strategic? Well, I'm not really sure, but I mean, what kind of intuitively what I want to say is they don't form beliefs about their opponents and then best respond or quantally best respond to those beliefs. So they do something else. And the literature actually makes it really easy for us. It almost always says these agents just uniformly randomize. So let's say they uniformly randomize for now, although we'll revisit that in a moment. Then, and now importantly, there might not actually be any level 0 agents in the world. This is just kind of maybe a construct in our mind. Maybe they really exist, maybe they don't. Now, a level 1 agent is an agent who knows about the existence of level 0 agents and behaves strategically with respect to them. So a level 1 agent best responds or quantally best responds to a level 0 agent. And there might also not be any level 1 agents in the world. That might also be a construct. A level 2 agent is an agent who knows the true population distribution between level 0 and level 1 agents and best responds to the mixture of what those two agents would do. And so on. We can climb the hierarchy however far up we want to do. And then the cognitive hierarchy's prediction in the end is going to be the true population proportions of all of these different agents with what they would each do. And it's going to mix those together and say that's my probability distribution over the action that an agent would take. Notice this isn't a fixed point calculation because we're not thinking about infinitely smart agents reasoning about each other. This is a kind of behavioral prediction. And notice also that this model is going to have a few free parameters. It's going to have a parameter for how do I trade off utility differences. When I said if they're close, they get almost the same probability. What's that kind of closeness parameter? And what are these true population proportions that I talked about? So those are parameters that I'll fit from data. In work that James and I did sort of a decade or a bit less ago, we showed that explicit models of level 0 agents can really help. So, you know, maybe not too surprising for a computer science audience, but the economists really don't like to think this way. The economists really want to believe that there just aren't any level 0 agents, so it doesn't matter how you model them. But I think we all know about people that there really are some non-strategic people in the world. And so it's particularly important to think about what they actually do. And uniform randomization is a pretty terrible thing to do. So that's probably not what they're doing. Furthermore, even if you don't believe in the existence of level 0 agents, changing the level 0 specification also changes the definition of what the upper level agents are doing, because that's what they're responding to. So getting this right really matters for the model. And James and I basically combed the cognitive psychology literature, trying to find different sort of cognitive biases that people might have that would be non-strategic. And we made sort of compound models combining these different ideas. And then we sort of tested them all on experimental data and tried to see which ones were predictive. And we tried lots of beautiful models that we thought sounded awesome and were psychologically plausible to us, but they didn't work because we had to actually describe real people's data. So what I'm describing here is what actually did work, to my sadness. It's not too bad, but some of the other stuff was better. But these models are binary features. So they just look at the actions in the game and they say, is this action the best in the deterministic worst case? Yes or no? If yes, I'm going to allocate a certain amount of weight to that action. And if no, I'm not going to. Does this action contribute to my own highest payoff outcome? If my opponent magically did something that would get me to that outcome, which might be a dominated strategy, might be ridiculous, but nevertheless, does this action contribute to my own highest payoff outcome? Does this action contribute to the least unfair outcome? Maybe there's another one that's almost as fair. Doesn't matter. Only yes or no. Is it the least unfair outcome? And if the game is symmetric, would this action be best if my opponents copied my strategy? So we take these four things and then we take a linear weight we learn a weight for each of these concepts plus one more sort of dummy weight. We add up all the weights on all the actions and renormalize them, and that's our prediction for level 0. And then we still have these other parameters for level 1, 2, 3, and we end-to-end learn both of these things at the same time. So we learn the weights of the level 0 model and also the predictions of the upper level models that react to them. And when we do these things together, using our new loss function that we've now realized we should use, here's what we get. So these little bands are error bars. And here I'm showing you uniform distribution with a quantital cognitive hierarchy and a linear model. Actually, I guess only using two. This particular one's only using the first two of those features. And you can see that it's a statistically significant improvement in loss. Okay. So then about a decade ago, and I realize this feels like a walk down memory lane, but this is all stuff you need to know to get to the thing that we've just done now that I want to tell you about. About a decade ago, we came up with something called GameNet, which might also be independently interesting to you, even if you don't care about some of the other stuff. So this is a neural network architecture that tries to just learn level 0 specifications rather than having James and me make them up and test them. So we have, this is a funny problem. We want to take a game of arbitrary size as input And we want to output a probability distribution over the number of rows in that matrix of arbitrary size. So we need some neural network architecture which is going to be scale invariant and also permutation equivariant. Because if I permute the rows and columns of this matrix, I don't want it to do something entirely different. I want it to give a permuted answer. And so we came up with an architecture that does all of that, where you actually pass in matrices and it learns one weight per matrix. So the nodes in the network really are operating on matrices rather than operating on scalars. Today, you could equivalently implement what we did using a sort of one-by-one graph convolution. That's not the way we thought of it at the time, but you could do that now too. But anyway, we have a neural network architecture where you can pass it in a game, or really what I'm showing here is a utility function for player 1, a utility function for player 2. It computes maxes in the rows and the columns, has weights on all of this stuff, and then ends up having a bunch of layers feeding forward, reasoning about the game. And in the end, it soft maxes out whatever these functions that it learns in these intermediate states, takes a convex combination of them and makes that its prediction. And that whole thing is our level 0 prediction. Then we can stack quantal response layers on top of it as well and learn the whole thing end to end. And so here's what we do. The first one, so now I'm showing you error bars with a 66% confidence interval in the middle at the thick bar and a 95% confidence interval in the skinnier bar on the loss function. And here I'm showing on the same loss that you were seeing before. And I'm showing you GameNet only in its level 0 specification, GameNet with also level 1 agents, also level 1 and 2, also level 1, 2, and 3. And you see that GameNet already does better than linear 2 plus quantal cognitive hierarchy, even if I don't allow the agents to be strategic, even if they're only being level 0 agents, which is surprising to us and to our economics reviewers who think we're wrong. And once I add one level of best response, it gets better yet. It gets statistically significantly better than our previous model. And when I add subsequent levels on top of that, it doesn't get any better. And this is surprising to us. And in particular, and now we're getting to new work that I haven't presented before. This led us to wonder, GameNet has a pretty expressive architecture. I told you it was a level 0 architecture, but should you believe me? Maybe this crazy neural network thing is sufficiently expressive that it can actually express strategic reasoning and not just level 0 reasoning. And if so, then maybe stacking more explicit reasoning on top of it has really diminishing returns because you've already got the power to represent that in the first place in the architecture. And how would we even know? I mean, in a neural network, I can't really point to something and say, that's the part where it's being strategic. So how would I even reason about whether this architecture is or isn't capable of being strategic? Well, we had to turn to theory here. So we went down the rabbit hole of writing a couple of theory papers to try to positively express what it means for any behavioral model to be strategic or non-strategic, so that we could then certify theoretically which category we're in, which again might be something that could be of interest to you in domains beyond this one. And the theory's a bit involved, so I'm going to do this at a very high level here just to give you the punchline. But I'll say that a behavioral model is strongly strategic if it coincides with quantal best response to some behavior which is itself dominance responsive. And dominance responsive means if you change the payoffs in the game to make something dominant, it'll play that thing more. So the level 0 agent is doing something that's not insane, that looks like it cares about its own payoffs to some degree. And the behavioral model itself is reasoning about that kind of agent and best responding to it in some sense. So that's maybe not the only thing that you could consider strategic, but I think you would think that's a sufficient condition for being strategic. And if you agree with that, then you'll find this theorem to be sad for us, which is that GameNet in its level 0 specification is strongly strategic. It's able to represent quantal best response to the max-max strategy that I told you before, which is dominance responsive. And so that means that the things we told our reviewers in our previous work, that this really belonged as a level 0 specification, were misguided and wrong. And really, in fact, this GameNet architecture is too strong. So now we want to try to repair this problem. And also in our theory work, we characterized what we call elementary models, which is a class of behavioral models that we can prove are non-strategic in a formal and strong sense. They sort of pass a sufficient condition for being non-strategic. And fundamentally, the way it works is you take a game, and for every action profile in the game, for every cell in the game, you apply some function phi, some function from the number of players in the game. So like if it's a two by two game, it's a 2-player game. For every cell in the matrix, you would apply some function of 2 real values and map them onto 1 real value. And it has to be non-encoding in the sense that it doesn't do sort of bit smuggling so that you could just invert the operation. So it has to be some non-invertible function. And you, in doing this, you take your matrix, which is a matrix of tuples, and you map it into a matrix of scalar values. So the idea is you're throwing away information here. You can't keep track of both players' payoffs. And if you can't keep track of both players' payoffs, you're not able to best respond because you can't both reason about what the other guy wants and reason about what's good for you, because these need looking at the different values in different ways. So you in some way take this potential matrix that collapses information from your game, and then you get to transform it non-linearly, arbitrarily, however you want. Once you've thrown the information away, you can learn any function you want of the potential function. And any model that is based on a structure like that is incapable of representing strategic performance. So we decided to build a neural network architecture that actually followed this recipe. So we made a neural network architecture that maps the utility functions to various different elementary models, and which are these blue boxes here. So each of these things is taking the 2-dimensional game here, the double sets of payoffs in every cell, and turning them into a matrix that only has 1 payoff in every cell by applying element-wise the same function in every cell. And we can learn what that function is, but it has to somehow apply the same function everywhere. Then once we've done that, we can basically run the same kind of GameNet architecture that we ran before on those potential functions. So we can then do some kind of arbitrarily complicated deep learning thing afterwards, knowing that we've thrown information away. And finally, we can take a convex combination of all of those things and boil them down to a single prediction. And we're going to call that a level 0 specification. And now, unlike what I did in the game network, this really is a non-strategic level 0 specification because our theorem applies directly to this. This really has to be a non-strategic model. And so here's the kind of punchline results figure, easy to show, hard to generate. What it shows is, so the top 4 lines are what I showed you before. First of all, you see that if I only have the level 0 specification here, it's terrible. It's much worse than GameNet was. And that's a good thing. It means if all you have is level 0 agents who aren't reasoning strategically, you can't do a good job predicting human behavior. People really do think strategically. If you then add these quantal response layers on top of the same, well, I guess you're fitting it end-to-end, so it might be different, but the same architecture of a level 0 model, things get much better when I add 1 level of best response on top of that, in fact, equaling the GameNet model. And we're not quite so sure why things get worse as we add more layers. We think we're probably overfitting here because we only have 26,000 observations in our data set. That's something we're still looking into, but we certainly don't see gains. But we're quite happy that this new model achieves the same performance as GameNet while being much more economically understandable because it really appropriately factors the level 0 agents from the other agents. And these green, so I've just told you about the blue bars. The green bars are the same as the blue bars, except I clamped the potential functions to those same 4 values that I showed you before that we used in our previous JER paper. So rather than getting to learn any potential function I want, I force it to represent those 4 potential functions that we knew about from past work. But in the past work, which kind of corresponds to those vertical dashed lines, we just learned linear models in those features. Here we then get to do some crazy nonlinear neural network thing on top of all of that. And you see we get, again, statistically significantly better performance by working with these nonlinear models, even when we use features that are interpretable. And the real advantage for doing this is not so much for performance, but it's because we actually understand what those features mean. So this now gives us a model that we can really understand. We can look at the weights that the model assigns to how many agents belong to the different levels, how strategic are people, and how much weight does the convex combination give to these different cognitive features, cognitive science features that the level 0 agents use. And we can actually get economic insight from all of this. So that's it. So elementary net then is this bridge between our theory about what a non-strategic play would look like and this kind of deep learning architecture, which is really able to give us certifiably level 0 performance and specifications, and then higher level models on top of it, and achieves kind of the same performance as we've seen in the past. We have various future directions we're thinking about trying to interpret more from the fitted parameters, trying to inject more complex potential functions, and looking at alternate specifications of strategic behavior other than just this QCH that we're stacking on top. But overall, I think this gives you a bit of a recipe for something that I hope, even if you don't care specifically about this problem, you can see ways you might be able to inject it in some of what you care about. That leaves me with 2 minutes and 30 seconds for the second part of my talk. And so I just want to tell you what it was. I'm not going to try to give you the second part of my talk in 2 minutes and 30 seconds, but it's cool. So I want to tell you what it is. So we've done a couple of papers that have been really laborious, both to build the system for and to run experiments for, to try to understand how economically rational large language models are. Thanks to all these co-authors who did this work. And basically the idea is that if I want to build an agent out of a large language model, I really want to know that the large language model is reasoning appropriately, even when it's a bit out of distribution on the kinds of problems I have. And what we think is the best thing to do is to look to economics, which has thought a lot about what rational decision-making ought to look like, find different kind of elements of rationality, which are the kinds of ideas that a rational model would be able to understand, like understanding the axioms of expected utility theory, not necessarily being able to tell you what they are, but being able to make decisions in a way that's consistent with them. And being able to reason about aggregating preferences in the way that social choice teaches us about, being able to reason about trading off supply and demand in the way that microeconomic theory tells us about. So overall, we built a taxonomy, which you can sort of think of as an entire microeconomics textbook for large language models that takes kind of the economics curriculum and breaks it down into many, many bite-sized little elements of rationality, each of which we use large language models themselves on top of kind of scripts to be able to instantiate it in 10 different domains. So we can ask questions about healthcare or about job seeking or about grocery stores. We can instantiate it at different levels of difficulty, and we can instantiate it in different persons. So like in the first person, asking about yourself, asking about another person. And then we can randomly sample thousands of different sort of semantically similar but syntactically different questions and present all of them to large language models so that we know that it isn't overfitting from data. And these numbers here are the number of different elements of rationality that each of these different modules has. The ones on the top are kind of algorithmic game theory kind of topics, and the ones on the bottom are sort of microeconomic supply and demand kinds of problems. And the punchline, you can look at this URL and this QR code if you like. This is a live system that you can actually play with. You can get all of the data. You can see the results of all of our experiments. And you can add to it, you can tweak it, and just find you can sort of look at the side, which is part of this web interface that we built to get a sense for kind of the sorts of questions that we have in this model. but you can put LLMs through their paces on a really wide range of strategic decision-making problems. So I'll just leave it here. If I had more time, I would tell you how they do. I guess I'll tell you a little bit. O1 is really good. It still doesn't nail everything, but it's way better than GPT-4 was, 4.0. Everything else was pretty bad at the higher level economic reasoning tasks, and there are some really consistent mistakes we can find about perspective taking, about susceptibility to cognitive biases, like for example, an endowment effect. We found that they could be really susceptible to endowment effects. And as models get smaller than the very biggest frontier models, they become terrible fast. So if you think that you're going to build a rational decision maker out of a model that you can download and run on a computer that you control yourself, you might have to wait a couple of years, because right now they're really not there. But more broadly, this will give you a tool that you could use to assess your model of choice as things continue to change and figure out when you think it's ready for prime time. Anyway, thanks for your attention.
Any questions?
Yeah, you guys did a great job of interrupting me when I was talking.
If we do, oh, okay.
It would not be possible not to have questions in response to that.
Excellent.
Well,
Let's-
thank you very much for a very interesting and intriguing thing. I read a bunch of your stuff on Quantles, the Quantal stuff, maybe a decade ago.
Mhm.
And so it's nice to get an update. Perhaps the stuff that I would like to ask about is something that we should actually take some more time offline to discuss.
Mhm.
But I've been critical of many of the ways that game theory has been applied in practice, even while being convinced that it's a very powerful and valid body of mathematics, on the grounds that not infrequently the utility measure is misdefined. And so in particular, I focus on the role of trust, and trust being considered as a capital asset for the decision maker. And so if what you do is choose to maximize your utility, when your utility measure does not account for that trust capital asset in any way, then it's going to say that the utility maximization action is going to be terrible. And you alluded to this at the beginning, saying that game theory often gives wildly counterintuitive recommendations, which I totally agree with. And I think that there is a reason for that. My argument, and I don't know whether, I don't think you were here for my previous talk, but
Sorry, I was not. Yeah.
we can't all understand everything that everyone else is doing. There's just too much.
All I can tell you is that being at your talk would have been a lot nicer than what I was doing. So
I am sorry for you.
yeah, it's all good.
But, the thumbnail is that society depends on positive sum outcomes to most interactions, which means cooperation, which involves vulnerability, which requires trust, which requires ways of assessing trustworthiness. And so if trust is omitted from the utility measure, you have greatly increased the likelihood of making at least counterintuitive and maybe actively bad decisions. Does that?
All right, there was a lot there. I missed your talk, but I feel like I got some of it right now. Let me just say a little bit about that, and then maybe we should transition to the panel.
Yeah.
And this sort of feels like maybe already beginning to transition to the panel. But let me say, first of all, I'm very sympathetic to what you're saying. I think it makes a lot of sense. I'm not sure that I would single out trust in particular as the only ingredient that deserves particular focus, that people's perceived utility experiences differ from what classical theory would tell us. More broadly, I think you're pointing to the fact that if you tell somebody what their payoffs are, you haven't always told them what their utilities are. Right? If I tell them you're going to get, a certain amount of money or something in some outcome, you don't know. For example, there's a lot of behavioral game theory work on what's called other regarding preferences that says, I care, all things being equal, about you being happy. And so I actually experience some positive utility just from knowing that you're happy. Now, of course, I'm not a saint, so I experience even more positive utility from me being happy. But it's not nothing. And so if we don't think about this, then we don't understand things like, why do I tend to like fair outcomes? I think that the thing that you're pointing to about trust is maybe particularly relevant in repeated interactions, where trust can sometimes be a placeholder for the likelihood that the repeated interaction is going to continue to work out well. And there can be sort of folk theorem style constructions that kind of make that explicit in the model. Or, if you look at the Nash equilibrium of the entire interaction rather than the stage game Nash equilibrium in the repeated interaction, some of these problems about trust go away, because trust really turns out to be a way of lubricating stage game play from one phase to another, rather than needing to be something that gets played across the whole game. You have something to say about that?
Specifically about repeated games and stage games, that I would interpret trust as being a more compact and concise way of representing some of the stuff that is otherwise computed in an expensive and not very robust way by analyzing the repeated game.
Yeah, great. I think that's exactly right. So I think, repeated games, we know from the folk theorem that the kinds of strategy spaces become exponentially big and really unwieldy to deal with. And maybe, we as humans tend to have some kind of placeholding intermediate quantities that we use to reason about these things. And something like trust is a great example of such a quantity. Let's leave it there, but thanks for the engaged feedback.
Yeah. Let's go to the last section, the panel discussion. Okay. We have a four.
That's a way to discover the reward. Coming on the line. Well, seeing the panel that we had, Maria was up there and we had Katia and I were piling on.
What's wrong?
So we've been having this panel. I think like probably. To discuss. Okay.
Okay. So let's go to our last section. Maybe we have several questions we want to discuss. So the first question is what is the most important fact when we build a mutual understand human AI architecture?
Particularly for those of us who are wearing stupid face masks.
But whoever wants to answer, all of us answering every question, but sometimes we may not,
I think you just heard a lot about my thoughts on architecture, so I'm not going to say anything more about this one. I'll let some of these people get a word in.
Yeah, so I don't know what you mean by architecture. So you mean a neural network architecture in terms of how many layers it has and all that, or anything else? Because architecture is so vague that I'm not sure, it's a kind of.
Yeah, that's for example, we want to build a human AI agent mutual understand the system. What kind of most important fact?
Well,
Like trust, like
well, first of all, they need to have a common ground to understand each other.
Yeah.
If they don't understand each other, and I speak, Sulawesi and the other person speaks from Mars, very difficult to even
Yeah,
start the interaction.
Yes, no, that is the question. It means the common ground, what kind of the key element we need to consider when we, build this common ground, when we.
Maybe you'd like to use this microphone.
Yeah, so the common ground, yeah, this might be.
Okay.
People at the back still might need it, I think.
So,
You can just sit there. That's the smart.
yes,
That's attached to the floor, so I think you're gonna have to sit there.
Oh, okay. Wait, this doesn't work?
But I'm saying you can also use it when you're.
Oh, okay. Okay.
works very well, but anyway,
Yeah.
does it work? Yeah, a little
Yeah,
bit.
yeah, yeah.
So what we are talking about, what is the most important architect, in other words, characteristics, for example, for building a human agent interaction. And I answered one of the, of course, important things is common ground in the sense that they should be able to understand each other. And now the question is, what are some of the elements? Of course, depending on how they communicate, they should be able to understand the tokens of communication, their meaning, right? If I say a table, we both mean the same object, right? And also, I think very important thing is to have some, I wouldn't say norms, but some ways of actually structuring the interaction and some ways also of, I would say, common experiences or experiences that I can relate to you and you can understand and you can relate to me. And when you make something, we can both, kind of understand. There are others, but I think these are going towards the understanding part to start with and the reasoning and so on. So that's a different, longer story.
I don't like humans, so I go to the next question.
I like humans. No, I even like agents. But human society has evolved over the last many thousands of years. And some of that has been biological evolution. A lot of that has been social evolution. And it's also been the accumulation of knowledge and norms and a huge number of other things. And so we live in a very sophisticated society that we only partially understand. And so when we start building a system that might contain AI systems, and inserting those into a complex feedback-driven system, our culture, that has worked reasonably well, obviously there are problems, we need to understand how the current system works. And we need, or at the very least, we need to draw on the knowledge that we as a species have learned about how our culture works. And so, I mean, I point to the example of trust, but in the course of my talk, I had a slide that pointed out a book by Michael Tomasello, which talks about certain kinds of biological evolution that make it cognitively possible to share intentionality, so that you and I can cooperate by creating a sort of virtual third person we might call we. And we can make a plan for we who uses each of us to accomplish some goal. And then there is collective intentionality where the we is the whole community. But then we also have processes of cultural evolution whereby we discover various kinds of knowledge, and that knowledge is transmitted and accumulated over generations so that we have a very sophisticated body of knowledge to draw on that none of us, no matter how smart we are, could ever come up with on the spot. There just isn't enough time. So I think as we start looking at what it means to have AI systems as part of our society, then we need to be able to say, how does society work? If you want to have an AI system in a car, you don't just sort of hook it up so it can turn the steering wheel or step on the pedals. You actually have to do some fairly sophisticated reasoning about the situation that you're in. And I fear that people are building artificially intelligent systems and wanting to insert them into a complex social structure, complex societal structure in a way that could very easily do a lot of damage. I could say more, I'm sure.
Okay, okay.
Okay,
So,
I'll start with the next question and then I'll pass. So the next question says, what do you think? So,
yeah. So next question will be more related to the first question. Just what do you think about the right now we created an artificial social system like the robots becoming the member or partner of us and integrate into human society in the future.
yeah, so talks about robots, so that's I can talk about that. I think they will. Sure, yeah, take it. Yeah, they will become more part. I mean, there are already, hospitals, nursing homes that have robots that go around, ask questions to the patients, and so I think they will become part as soon as they become more useful. Right now, they're still very limited in the ability to do things. But some of the tasks are not that difficult. LLMs will help because they can chat with people instead of having to do other things. And I will expect, there will be at some point a robot that you can say, I go out shopping, I bring my stuff home, I say, put it in a refrigerator. Right now it's impossible, but it will happen. Or, prepare the table for me. I mean, I don't see this as being impossible.
I guess I feel like this question is in many ways asking the same thing as the first question, or at least we're choosing to interpret it that way. So let me kind of reflect on both of them. I think it's very hard to cooperate or partner with something unless you're able to understand what it's going to do. And I think that's sort of a big lesson of game theory. In a sense, this is sort of Ben's idea of trust, except maybe it raises it to a different level of abstraction that says, if I know that you're just going to try to kill me, then at least I can trust that I know that you're going to try to kill me. Then I know the right way to respond, right? So as long as your behavior is going to be predictable from my perspective, then I can figure out how I ought to interact with it. And it's really the hardest to partner together or to be in a society together when our behavior is not intelligible to each other. So to give the example of being a Canadian in the world right now, the United States has gone from being very intelligible to us to not very intelligible to us at all. And that makes it very difficult for us to partner, right? If everything is kind of uncertain and chaotic, yeah, for you too, but I'm just giving the example from my own experience. But you see that if you have a clear sense of what to expect, then you sort of know what to do with it. And so I think that's sort of related to this idea of trust, but I think that's sort of how a game theorist thinks about these things, that the worst thing of all is not knowing what's gonna come. And I think large language models have made this much better by being able to explain what they're doing in terms that the regular person can understand. They've also made people really distrustful because they sometimes don't do the things they're saying, or the things they're saying don't sometimes make sense with reality. And the kind of sense of betrayal that people have about things like hallucinations, I think, are grounded in the fact that the model has become so intelligible. It's able to say something that really seems to make sense, except that it doesn't quite make sense. And so I think that sort of uncanny valley of intelligibility is a particular issue when it comes to human-robot interaction.
Well, I would be a little bit more humble and say that I don't think that vision problem has been solved. to start with. So when we have cluttered environments and so on, or we have glare, we have snow, we have fog, it's still an open question about what can I see and what can I expect. I mean, what can I see as a self-driving car in the fog, for example, to avoid? Okay, forget about society and all these things. We are still, when we are talking about understanding, if there is a thing in the fog and it doesn't see and it tells me something, whatever, or it says I cannot see, then I need to help it or something. First of all, I need to understand what it's telling me. That's what I was talking about, that the same things should mean the same thing. I say a table, you don't say cabbage. You don't think I'm talking about the cabbage. So all these things we need to be realistic about, as Maria is saying, what the current things are, but we need to start from sensors, from senses, build up, and then we build up the rest of, the individual, the society, and all these things. Sometimes the big fluffy things are easier. LLMs say all kinds of things. Then the actual, one is 4 greater than 3. You ask it 4 times, and three times out of 4 may answer yes, but the 4th one, it may say no. So if probabilistic arithmetic now is probabilistic, then we are done for, right? And so we need to be thinking about these kinds of things to start with and assure that the foundations are correct, right? Let alone the hallucinations and all these other things. But just
Okay, we can move to next questions.
Okay.
Oh.
The next question will be for you.
Oh, I just said one little thing because this question was talking about incorporating AIs into our society. We all here have spent our lives working on artificially intelligent systems that are based on digital computers. But there's another whole class of artificial creatures which are goal-oriented problem solvers and utility maximizers, which are corporations of various kinds. And not only profit-making, but nonprofits, governments, churches, other kinds of collective intelligences that have existed for a small number of centuries within our society and have accumulated control over a large fraction of the resources of our society. And furthermore, they make decisions based on what many people consider are overly simple utility measures. And so I think we are sitting here thinking about the challenges that may arise as our digitally based AIs get more powerful and start to become more integrated. But here are another very large, very powerful collection of artificially intelligent agents that are already having major, major influence on human society.
Maybe just one conclusion. Current
So
AI and
difficult question.
yeah, current AI and I mean the technology just reflect the human natures. Maybe that is the key problem for us, I believe. I mean we create current technology development and current AI just is kind of a mirror reflect the human natures.
are you asking? Is it a question?
No. I just
Statement.
maybe just yeah. So the next question is what should we do if we build a strong AI agent like the maybe self-consciousness, the self-awareness agents, such as the positive agent like Ultron or Data, and the negative agent like the Terminal or Skynet. What should we do?
Yeah, I really like the last thing that Ben said, and I think that it's the right way of thinking about the answer to this question. I think that I promise I would have said it anyway, but I love it, and I think he's exactly right. So I think it's not very helpful to look to science fiction as a way of getting metaphors for understanding how AI is going to work. I don't think we're going to be living in the age of Ultron anytime soon. And I think that distracts us from the age that we are just about to live in. I think the age we're about to live in is the age of the artificial corporation. I think AIs, we already have experience with super intelligent agents, agents that are more intelligent than humans that can take actions that are too complex to fully understand or reason about. And those are organizations, businesses, corporations, the international community for the Red Cross, Japan. These are, superhuman intelligences. And I think once we notice that, we actually have a lot of experience with dealing with them. Japan is incredibly complicated, but we can, even though we can't fully predict what it's going to do, we can't understand everything that it does. We have a lot of tools that we've evolved over time for managing that complexity. We can audit it. It can enter into binding commitments. It can be regulated in certain ways. Maybe sometimes then it doesn't do the things that it said it was going to do. But generally speaking, we have this sort of body of tools for thinking about how to interact with something that's much more complicated than us. And so I think we're about to enter into an age where AIs are kind of like corporations. They're kind of like big, complex actors that we can't fully get inside their decision-making processes. But all the same, we're going to have a degree of transparency, probably a greater degree of transparency than we would have about corporations. And so I think trying to figure out how to manage that is going to be one of the really key challenges at the boundary between people and computers in the next decade or two. And I think all of this happens before, you have death ray lasers shooting from the eyes. I don't think that's the thing we should be fixated on first.
So let's see. It's a little bit unclear about LLM being like a corporation or a country, because the point is I can always switch the damn thing off, whereas I cannot switch Japan off, let alone, yeah. So there are some differences there. And also, it's not going to have powers. So it depends on what kind of powers we allowed it to have. We have allowed corporations to have particular powers. But again, I don't think that we are going to do artificial agents and allow them to have these particular powers. I mean, people are off their wall, of course, as we've seen throughout history and so on. They are very irrational in the common sense, not the economic sense. So anything is possible, but I don't want to think that anything is possible and I would have it. So the other thing is that even for these snarky and horrible corporations and so on and so forth, there are some regulatory agencies. I can see their books. I can say, okay, there is fraud, and so on and so forth. Now, for these large foundational models, I have no idea what their data are that is being trained on, and how what their vulnerabilities are, and what other things that may happen. I mean, I think that it will become sort of like more unmanageable, like, of course, social media, where anything goes. So it's social media are not like a corporation, but it is kind of in the aggregate, intractable, uncontrollable. And so if we let AI to be like that, I think it's more like the social media.
So let me just quick comment here. You talk about self-consciousness, self-awareness. I don't know. Can we really get to the point? I'm not sure. I mean, it's easy to use the, AGI, all these buzzwords. I'm not sure that I see.
Maybe we can use the just like when humans ask themselves who I am and what is my future, and that is the basic questions usually humans ask themselves. That which means we have maybe some kind of the self-consciousness. When we build a robot, someday they ask who I am and what is my future. That is the serious.
But
things.
it's not clear you should humanize things so much, right? I mean,
Yeah.
self-conscious restore makes sense for humans. What does it make sense for a robot? I'm not sure. So I wouldn't
Okay.
not use the same words.
I think I'll.
Okay. Okay.
Oh, okay.
Next, let's go to the next.
Actually, we're thinking about support the audience.
Yeah.
Good idea. Yeah.
Yeah. Does anyone have a questions want to ask the speaker?
In the meantime, I can ask you guys like a follow-up on
Yeah.
that one. So on kind of, I guess, like, all of you, like, there was a theme about trust and rationality and all these aspects, right? And so I wonder, like, what then, like, the ultimate agent, right, so that we want in our society, right? So what should it embody? There are also, like, different ethics and theories out there. So, like, whether it's the ontology, whether it's utilitarian and so on. But there are also sometimes conflicting, right, so with each other. And so the, like, how should we, in a way, define the agent, right? So, and how, like, in a way, we want to ensure, right, so that the agent that perhaps will do, right, so what we expect them to do, and instead of, like, doing something else.
Well, I think one of the first questions that we want to ask, first of all, we're not going to be talking about the agent, because there isn't going to be one, I don't think. And the question is, do we want to make agents in the mirror of ourselves, right? And so if that is the case, then of course we're going to have a lot of differences, like this human simulacra, right? We want to make specialists that play basketball better and doctors better or whatever. Do we want to have that? As a society, I don't think we have either thought about it or worried about it and so on. We are talking about these robots that we try to make them do something, like pick the cup without breaking it and things like that for now. And, navigate and locomote and do off-road driving and all these other things that people can do. But at this point, I don't think even we have these models down. But the thing is, do we want to make people in our own image, our own meaning as humans? I mean, that is an interesting question. And if we do, then that's one thing. Then they're going to have all the human foibles and all this. Or do we want to have this very sort of, shall we say, have integrity, having, all these things, the norms and the morality and so on. They're just sitting there, saying, look, you didn't do that correctly, right? Because I have a better understanding of moral thing, and they're going to be like our parents that say, look, you didn't do that. So these are all some things that we need to be thinking for consequences if we say one thing or another in terms of society, what we want about this agent. There are going to be many of them, not just one. So.
Well, I think that there is not a clear sense that artificial intelligence is going to be just like humans or just like corporations. And corporations are not just like humans, but I think it's illuminating to realize that there are three different genuses, if you will, of intelligent agents. Now, one of the things that I get concerned about is that I think Katia is right, that we would be very, very cautious about giving large amounts of external power to artificially intelligent digital agents. On the other hand, would corporations feel the same way? Because I think corporations, when they see it in their interest to deploy an artificially intelligent system in order to make decisions, for example, about people or transactions with other corporations, may make that decision in a significantly different way from the way people might.
And sometimes better, sometimes worse, because they may not have stereotypical biases if they are programmed, for example, not to, like people would. You are my friend and so on. And so we do this thing together. I don't know if these agents may or may not have friends, you know. And
But we have studied quite a lot about how difficult it is to avoid putting those biases into a system. That you can.
And this is what the point, we come back to the point about what data are being trained on, auditability on that, because we don't have any audit trails at all. And that to me is the biggest problem, right? I mean, even in the corporation, as I said, you can, if there is some auditability and all that. Here, there is no auditability.
Okay.
Sorry, I'm not sure that this
Oh.
auditability is such a critical thing. I mean, billions of data that they use to create those models. I'm not sure that that's a critical part. But limiting the control, limiting kind of things that agents can do, that to me would be important, right?
Well, I was talking about social media because I think that if, suppose a corporation or somebody says, okay, now I give 3 trillion examples that say the earth is flat and other things in terms of physics. What would this model then say? You ask it, the earth is flat. And nobody of us have saying, okay, well, you know, we take out all these things from fake pictures, from, these satellites and so on that show some curvature. Well, maybe this is not the earth. This could be something else. And what do your eyes tell you? Well, you're walking on a flat thing. The earth is flat. So don't say that there is no, problem with the data, right? I mean, you can imagine these things.
I think these questions are a little bit hard to engage with because they're asking us about a really, pie in the sky sort of science fiction future that we don't know, I think, enough about to say something intelligent about. I think most of what I think those of us working in this community think about is much more pragmatic questions about getting human robot collaboration systems to work in the world that we live in today. I think a lot of these questions to me are really questions about sort of political science and about law, about sort of regulation and about the social contract. And I don't especially think that we are, more well-informed on those topics than the sort of average person you might stop in the coffee break. But I do think that fundamentally our society is our own construction. We get to decide the rules by which our society will function. And I think we're now entering a period of negotiation where we're going to decide, as large models become agentic and become, capable of taking action and impacting us more directly, what our societies are going to allow. Like, are we going to allow them to work in healthcare domains? Probably not. Are we going to allow them to go around saying that they're lawyers? Probably not. Are we going to allow them to just construct houses that people will live in without following the building codes? Probably not. So, it's not just kind of, or maybe we will, who knows? But these are choices that we're going to get to make, right? And as Katia says, we can turn these things off if we don't like them. I guess the game theorist in me does say they're not all going to be under my control. So there are going to be people from foreign states that work very differently, throwing this stuff on the internet. There are going to be Ben's corporations taking actions that might not be the actions that I want. And so I don't think we get to do a sort of centrally planned design of all of this stuff according to sort of humanistic principles that we would like to see. I think to some extent we have to learn how to navigate the world as it is, but it's going to take us a while to get there, and I think we're going to figure it out as it happens.
But I mean, the control issue that you mentioned, the control issue that you mentioned, I think that's a critical one. Who is going to decide? Because, the corporation, whatever, somebody else will decide and we will lose control. I'm not sure there's any potential ability for our communities to say, no, you cannot do these things. Trust is one of the many issues that come into the picture here. I mean, if somebody comes up, a powerful system, everybody uses it, we're out of luck, right?
Okay, our audience has questions.
Next question.
Oh yeah, this is actually kind of connected to that one. So like I kind of agree to like as a society, it's kind of like especially that we're in this stage where we're kind of like transitioning, actually like questioning like how safe AI is to integrate like in our human society. I can also kind of agree it may vary like depending on the culture, on the government, and the country, like what are the kind of like priorities. And so like my question is like as experts like and seeing like the trends. So in the next coming decades, which industries do you think where we could possibly allow or integrate AI, in human society, which we think we could benefit from? So, and if we do, so what kind of regulations or interventions should be kept in place to maintain or, like balance in the system? So for instance, should we kind of like, allow AI in education, let's say in the upcoming years, things like those. And if we do, like, do you kind of think of some systems in place to kind of just regulate AI?
I think that depends on the type of, the type of role that they would have to play, right? So, for example, there are robots in hospitals, not just robots carrying, garbage or whatever it is, cleaning the room and things like that, right, in the home. But also there are systems that may help, for example, looking at X-rays and help the doctor, the radiologist, make better decisions, right? So we have already some of those, and they are in these roles of human and interacting with the robot as the robot or the AI agent that helps the person, perform better. We do have systems for target tracking. We have systems for whatever, right? So these are all systems that have, to some extent, they are sort of, I don't know whether you think that a vision system is an AI agent, but it is coming from AI. Right? So if it's able to diagnose better the X-rays, then it is already an agent that we have. So this is, we already have some of that. And so I think that sort of a more cautious penetration of these agents would be a wise thing for a society, instead of saying, this is great, let's let it now decide whatever, right? At least that would be my, if I were to give some kind of advice to a social whatever, I would say, let's incrementally and introduce them.
I don't want to appear pessimistic, but honestly, we will not have any control of what happens to those systems because money talks, right? And there's a lot of money there. So I think the only thing we can do is to try to get regulations, some kind of regulations, right? But I don't know, even those will be easy to come up with. So things we penetrate slowly in our society and we'll discover they're here, whatever they are. And I don't think we'll have much control, honestly. I don't know.
Well, we are a largely academic research community, including industrial research community. And I think one of the things that we can do to influence the direction of things is to help introduce certain concepts into the language that people are using to debate these things. And I think the question of super powerful AIs that are going to kill us all is not a terrifically productive way to do this, to introduce this into the debate. And I'm a big fan of this whole notion of talking about trust, because I think trust does play a very important role in people's ability to believe that their society, that they can interact in ways that are safe for them in their society. And so I guess what I'm doing by arguing for this is to say that should be an explicit term that we use when we're debating what to do about AIs, and to say who needs to trust what. And those are big questions. They have very diverse answers, but they need to be questions that are directly on the table in order to make decisions. Now, furthermore, we're in a very diverse society that includes an awful lot of powerful corporations as well as governments, and they are each going to make decisions largely without coordinating with each other in what they perceive as their best interests. So one of the things that we can do is to say, you may think that maximizing your quarter by quarter profit is in your best interest, but in fact, if you're willing to look more than quarter by quarter and start looking year by year or even decade by decade, you actually do need to pay attention to these, even just in terms of your own best interest. So the way you get people to behave in a certain way is to convince them that behaving that way is what they really want. And people like us can have influence on how people look at those questions. They may agree with some of us, they may disagree with some of us, but entering these concepts into the discourse, I think, is a significant contribution and is something that that does have an effect.
I'll just say something brief. I can see it's getting late and we should be winding this down, I think, but just in response to your question, which I think maybe we've strayed a little bit far from, I don't think we tend. I'm going to disagree. I think at least with some of what Katia said, just in the interest of having a panel that actually disagrees with each other. I don't think we're going to be auditing the training data that LLMs are trained on. I don't think it especially matters. I don't think it's very opaque. I mean, sorry, I do think it's very opaque. I think there's going to be a lot of information substitutes that can get you to the same place in different ways. And I don't think that's the lever that we're going to use. I think the way that we tend to regulate technologies is not by how they work, but what they get used to do. And so I think we're going to say, build your LLM however you build it, but it doesn't get to claim to be a lawyer. Like teach your kid however you want, but they have to cover the curriculum. I think we're going to just try to control these things in terms of outcomes and actions, not in terms of internal representations. And that makes me more optimistic than Maria was at least sounding there towards the end, because I think, regulating the inner workings of something is very difficult, but it isn't in principle that hard to tell, a mining company, you can't dump your tailings in the river. You might do all kinds of complicated things that we don't understand, but ultimately your actions, insofar as they step on other people's interests, are something we have a social concern for and we can regulate. And I think that's what AI, the interface with AI in society is going to look like in the next decade. I think we're going to start carving out rules about what sorts of things it's able to do without much discussion for how it works.
Well, this is what I was saying with respect to the vision system, for example, helping the radiologist, right? And so this is an AI thing. And yeah. Pretend. I mean, they're both of these things, right? So it's interesting on the one hand to talk about these things and seeing what they can do and say, okay, you can do this, you can do that. And that's one of the things that I think it's the rational thing to do as a society. And on the other hand, another view is to treat these things as you treat a machine. I mean, so if you're radiology, so whoever and have the responsibility on the company or whoever developed that thing, right? And say, okay, if your thing caused an accident, if your thing does not behave that way that society wants, then you are fined. It's like here is, an apparatus, mammograph apparatus, and if it starts giving erroneous things, then you say, okay, whoever made it, okay, you are going to pay a big fine, right? Now, these are very difficult to say about these things, but at least it's a beginning. You can say, okay, you're a machine also. An airplane is a machine. If I have the control, the control for the aircraft, and it's wrong, then whoever created the software gets fined, right? And so on. So I mean, that's kind of a simplistic thing initially, but I'm not sure if that can escape.
Just again, I don't want to be the pessimistic, but at the same time, I'm looking at it, right? So social networks, right? You all remember they came out from the computing community, wonderful. You can have your own news, you can have your blah, 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 and we see the results. Did we have any control? No. Are we going to have much control on this new technology? No, unless there are clear, strong regulations, which is not clear that they will exist and what they should be. Because otherwise, the technology is out there, people can use any way they want. Exactly, social networks, the same thing. So, but I don't see any signs that there will be strong regulations. So that's why I'm on the pessimistic side, but maybe everything will be wonderful. Who knows, right?
So let me take an optimistic position, because we have been watching evolution go on for many, many millions of years. And if we don't get this right, you know, well, you gotta, yeah, right. I know. Yeah, there should be a clue. You should read Italo Calvino. But evolution is going to take care of all of this. We'll either get it right or we'll get it wrong. And if we get it wrong, Darwin will come and take us away and the cockroaches will get a chance. And then we'll see whether sooner or later, after multiple cycles, we'll figure out how to do this whole thing. So that's my optimistic take.
Yeah, okay.
So, I think maybe in the interest of time, we can conclude with just for each of you, maybe a remark that goes back to the technical aspect, and just maybe inspire the young researchers that are here, and each of you perhaps can comment. Okay, so this is an exciting open research problem that I think it would be interesting to solve. Hopefully then some of the people here, right, so maybe try to address.
Yeah. I mean, one of the things that I would say, and in brevity and so on, there are many other things, but one of the things that I would say with respect to foundational models, because the other thing that we didn't talk about all these LLMs, foundational models and so on, is the energy consumption, right? So before we even let them take control of us, we won't have energy. We'll blow up the electric grid, we'll look at nuclear energy and so on and so forth. And with the climate change, that's a great combination, right? Going toward. So one of the things that would be very useful is to have, how can we have smaller models with the same predictive accuracy or whatever, with the characteristics of larger models? But they're smaller in the sense that we can train them faster, we can maybe audit them, and yeah, and also in deployment, right? We deploy them faster, but they keep their accuracy, their performance. And then the point is how we can make combinations of those then, right? And have more performance. So this is a technical aspect. You can do it, you can look at distillation, things like that. Anyway, I mean, we can discuss that, the technical aspects, but this is a technical thing and it's very important.
Well, on the technical side, I think trust, right, is very important. Get back to trust. I mean, there are a few things that you should really focus because have not been, very central in the development so far. So trust, and then of course, safety, and all those other issues are coming up, ethics. And so I think we should really think seriously and in a technical way. So I mean, again, come up with technical solution as much as possible, algorithmics or whatever, not just talk. I mean, sometimes we talk, but we don't try. I think those are all very good areas for research.
Okay, I'm not going to propose a particular technical area, although you're welcome to browse in my webpage and find various things along those lines. But a critical thing that I would like to urge everyone, particularly the younger people here, is that the world looks pretty discouraging. And I mean, I've taken a couple of groups out to lunch in the past while, and the world is pretty discouraging. And I think it requires each of you to say, I've got a life which I want to make a positive contribution with. Furthermore, I'm really, really smart, and I have one of the best educations in the country, in the world. And this is true of each of you. And so what is it that you can do that can help improve things? And even though things are looking grim, it's important to say, what is it that each of us can do that moves it in a positive direction? When I was growing up, the specter of nuclear war was everywhere. And our elementary school principals told us to duck and cover under our desk. And we've gone around and around various other crises, the Vietnam War, various other terrible threats. And what you have to do is to say, what can I do? And you have been given talents way above what many other people have been given. You have opportunities way above what many other people have been given. You face challenges. Sure, you face challenges. And those challenges are in some ways worse than the challenges that I faced. But you got to decide what you're going to do, and you got to understand the world.